In this video, we're going to do a very brief overview of homogeneous linear equations, and we're going to specifically look at the cases where we have real roots, but that's not going to make sense until after we're a little in. So if we have a second order homogeneous linear equation, that's what we've got right here. Right, it's second degree because we have second degree differentials, homogeneous because it's set equal to 0. What we can do is notice that our solutions need to be of the form y equals e to the rt, because we're basically looking for something where the second derivative looks like the first derivative plus the original equation. E is really the only function that's going to act like that. Okay, well, so let's just try it out and see what happens. If I take this y equals e to the rt, then y prime is r times e to the rt. And the second derivative, again, is just the product of that derivative at the top. So y double prime is r squared times e to the rt. Okay, well, let's plug that in. So we have a times r squared e to the rt. We have b times r e to the rt plus c times e to the rt equals 0. As you might notice, we can factor out e to the rt. And we're left with this. Now, e to the rt as a function is never 0. So it must mean that ar squared plus br plus c is 0. And I'll write that out just so that we're clear. E to the rt is not equal to 0 for any r or t. And we actually call this ar squared plus br plus c equals 0 the auxiliary equation. And what that's telling us is if we can solve that auxiliary equation, then we know what our solution looks like. Well, because we're dealing with a second order ordinary differential equation, we can rely on the quadratic formula. Right, so we can find the roots with the quadratic formula, and there are going to be 3 cases. So we have the 2 real cases, which is what I was mentioning at the beginning of the video. Either our discriminant is positive, they're 2 distinct real roots, and the solutions will look like right? Just thinking about what we had before, that y equals e to the rt. So our solutions will look like this. If it's actually 0, then we get a repeated root. Now, this becomes a little bit tricky. What ends up happening is these are the solutions. E to the rt, as we expect, and then a linear term t e to the rt to go with it. And finally, we have this complex. I'll look at this in another video a little bit more closely, but the idea is we're going to use Euler's or Euler's formula to rewrite e to the alpha plus or minus I beta into I shouldn't do this off the top of my head. Cosine beta t plus sine, and I've run out of space, beta t. And I'll confirm that. You definitely want to look that up. I'm fairly certain this is what it is. There is no e term, so it might be something like this. But basically, you're going to use the Euler's formula to convert it with cosine and sine. That's not the focus here. So let's just erase this for now. So we'll do one practice in this video, and I'll post this PDF. That way there are a few other questions that you can go ahead and practice with. Okay, so we have y double prime minus 5y prime plus 6y equals 0. Again, if we're thinking about this, we're saying, guess, I meant to write y. All right, we're guessing that y looks something like this. There might be a constant in front. So when we plug that in, we're getting r squared e to the rt minus 5r e to the rt plus 6e to the rt equals 0. All right, plugging in that first and second derivative, we're getting the auxiliary equation. Because again, e to the rt, after we factor it out, cannot be 0. So this part must be 0. Now, we could use quadratic formula, but we could also factor it real quick. And this is exactly what you would have gotten if you used the quadratic formula. We would have gotten r equals 3 and r equals 2. So what the general solution is going to look like? It's going to look like a linear combination of these two possible solutions. So what our actual any solution could look like would be something like, we might call it constant 1 e to the 3t plus constant 2 e to the 2t. And so these are all of the different possible combinations in our boundary conditions course. What will end up happening is we can solve for this C1 and C2. And just so that you can see it at the end of this PDF, we have a nice little summary of exactly what's happening. Solving second order homogeneous differential equations with real constant coefficients. You set up your auxiliary equation, you solve it, so it's this or factoring, if you can, and then you have your cases.